Welcome everyone. I am Avik Kar, TA of this course. I'm a PhD student at Indian Institute of Science. So welcome to tutorial 5 of this course, Reinforcement Learning. Today, our agenda will be the following. Last time we have seen value iteration. Value iteration algorithm we have seen will show it returns optimal value function, optimal value, and optimal policy. And then we'll discuss policy iteration. Also, we'll do the theory part of it. Also, we'll implement the algorithm in Python. That's the agenda of today. And these two, you know that these two are planning algorithms. Can any one of you please tell me what is planning algorithm? What do you mean by that?
It means that the expected rewards and the transition probabilities are available.
Yes. So planning algorithm is basically you know the system and design the optimal controller. And reinforcement learning is when you do not know all this information and still you want to learn the system or learn how to behave optimally with that system. So that part is not started yet. In week 5 lectures, the last part, the policy evaluation and Monte Carlo algorithm is introduced. So next day we'll start freshly with reinforcement learning algorithm without like planning. We are stopping today and we're finishing today. And from the next day we'll go with this planning algorithm. We'll discuss Monte Carlo algorithm and then TD algorithm or temporal difference, and we'll port those algorithms as well. Okay, so let's recall our notations. We have MDP. S is the state space. A is the action space. P is uh, the transition probability kernel. Mu is expected reward, and gamma is the discount factor. So this is infinite horizon. Discounted MDP. And we are denoting this tuple by calligraphic L. So P here we are imagining this is, assuming this is homogeneous. P is homogeneous. That is, P is a function from S to 0 to 1, such that PS A prime summation over all S prime is 1 and PSK S prime greater than equals to 0, which makes it transition probability final. And mu is also homogeneous. Mu is also homogeneous. Gamma is a constant between 0 to 1, excluding 1. And the objective is to maximize phi for policy space V. Am I writing in like, was it superscript or subscript in the last lecture, last tutorial? It was subscript. And this is equals to summation t equals to 0 to infinity expectation gamma raised to t times expectation RT. Even is 0 is S and AT is taken according to the policy pi. This thing we not write and denote this expectation by E subscript pi. And this for all S we want to maximize. And we have given you this algorithm. So the algorithm is in short I'm writing. Initialize so that is the step we are operating, and for all is state space. And we update this value. Sum over is prime of the next state forward. And then we construct a policy which is basically the maximizer of these things. PK is the policy at this stage. PKS is basically arg max of this entire thing. And then if Pk equals to Pk minus 1, or another condition was that Vk minus 1 less than some epsilon, so infinity no, is less than some epsilon, then break. And then return Pk and Vk, these two functions. Well, so this was the algorithm, and we want to prove that this Pk and Vk. Actually, I am not considering this second condition. I am erasing that. I'm only keeping if Vk equals to Vk minus 1, if two consecutive policies are same. Second condition I'm erasing. That is not, may not give us the optimal policy. That will give, you can assure that will give some excellent optimal policy, but we are not sure about the optimal. So let us define something called Bellman operator.
I think we forgot the gamma factor in the equation.
Oh, did I? Oh, yes, yes. Thank you.
So in that equation, basically,
Yes.
the second term, right, after the plus sign.
I cannot hear you properly.
Yeah.
Which?
So the second term, well, not the second term, the one which follows gamma. Can you elaborate a little bit on this one?
This one.
Yeah. Yeah.
Okay. So say, so now you're yeah.
So let's assume at some stage we have some values for each of them. Each state we have some accumulated some values. Now can you elaborate on that?
Yes. So at when you are starting kth iteration, I mean here you are here, you're you're starting your kth iteration at time, or better to write at iteration k, at iteration k, estimate of your value function that you have, estimate of value function is Vk minus 1, right? When you are starting. So using that estimate, you are trying to compute you're trying to update your value. So suppose you are at
So
say
one question is so the if you look at the two terms combined, the first one is the mu of S comma A, I guess, is what is the reward you will get immediately plus gamma times the discounted future reward, right? So the second
yes,
term isn't the future reward of
yes, it is the future reward, and that is expected future reward. Now you are taking action sorry, at state S you are taking action A, and with some probability you will land up some state S prime. Now at S prime you have already have an estimate of the value at S prime. So basically you are multiplying with that probability. So you are taking an expectation. So you do not know where you will be at next state. So you're taking an expectation of value.
Okay, so it is basically moving out from S to S prime discounted by gamma.
Yes, yes.
Okay, okay. And so once we move into S prime, the current estimated value of the value function over there is that Vk minus 1 term.
Yes.
Okay, okay. Makes sense. Good. Thanks.
Okay, so let's come back. Uh, we'll define something called Bellman operator. So what usually is called an operator is, so we know what is function, right? So this is your domain and this is your range. A function maps takes a point in domain X and a function F maps it to a point in range, which is Fx. And these two things, domain and range, can be different. Different as in, say, this is real and this can be, say, complex or even something complicated. Say complex race, I mean, n-dimensional complex plane. Okay. So these are not required to be the same. So we call something operator when this domain and range, better to call it codomain, because range is only the set of points where uh, a map from domain exists. So domain, and let us call it CD. So when these two are equal, then we call this map as operator. So what is Bellman operator? Let's say V. This V currently we are discussing about is not a not value function, but we'll actually apply it on value function. So value function has to do something with it, but uh, currently we, in context of defining the operator, we are not talking about value function. V is the function from state space to reals. Then the operator TV is also a function from state space to reals. So this is operator because the operator is taking the function to the same space. Space as the functions, set of functions from state space to real number. Well, so how do we define that? T V X is max and right is so now you understand, right? This has something to do with this iterations. So this is exactly similar. I mean, VK and VK minus 1 is replaced by this V. And okay, so when you are doing value iteration, what you are doing? You are taking V0, you are starting initializing V0, right? Initializing V0, it's all 0. And then you are applying operator T, you are getting V1, and which is equals to TV0. Then you are again applying operator T. You are getting V2, which is basically T of TV0. This we can write in shorthand T square V0. This is not exactly square. It just it just means that you are applying the operator on V0 two times, and so on. And we are saying that it will, if we keep on applying this indefinitely, then we will land up to the function V start. That's what we define the optimal value function, right? V star. And eventually you'll get the optimal policy as well. That's what it means, right? Now, we'll prove this that if we apply this operator, I mean, again and again, the operand that will converts to something, and that something will be the optimal value function. Okay, so we'll prove two things first. One is monotonicity of this operator. So lemma 1. So this applying this operator again and again is clear, right?
Yes.
So for any function v, which maps from state space to reals, and v prime such that v is always less than equals to v prime s for all s in state space. And for okay, so here I need something else. I need to define another operator. So when we prove policy iteration, that will come handy. We define operator called T pi. T pi. T pi v, which is mu of s comma pi s. That is, we are taking policy using policy pi. T is comma pi is prime. V pi, sorry, V is prime. So here I'm considering this pi is deterministic, but it's not necessary. You can assume pi is randomized, and you have to take expectation or modify your transition probability accordingly. So this is another operator, and where we are fixing the policy. So, but one thing is true, that this is stationary policy. So all the steps we will apply this pi for any stationary policy. Pi So Tk means this operator applied k times. Tk Vs will be less than equals to Tk V prime S for all S in state space for all k equals to 1, 2, and so on. And similarly, T pi k V S that will also be less than Tk pi V prime S for all S for all k 1, 2, and so on. So this is a proof for all k from 1 to 1, 2, 3, 4, and so on. So what we can do is we can just apply induction, and it's very easy to prove. So I'll not. So base case is already given that uh, we base case is the statement itself. So this is base case for k equals to 0, and assume induction hypothesis. Then KV, this is equals to max range R S K plus. Did I write gamma here? Oh, again, I have forward gamma here. Yeah, please add in this definition of the operators. So this is here I can replace this TKV, TKV prime S prime. My bad. TKV S prime. This TKV S prime we can replace with TKV prime S prime, because by induction hypothesis, uh, this TKV S prime is less than TKV prime S prime, right? If all this prime and V and all is confusing, let me just write OPT max A TK V prime S prime. And this is exactly the definition of T uh, T TK V prime, right? Okay, this is evaluated at S. So yes. So this is exactly T K plus 1 V S, and this is basically T K plus 1 V prime S. Right. So this proves the induction step. This is proof. Fine. So this monotonicity lemma is done. Now we'll prove another lemma. These two things are actually will be used as tools. Lemma 1, Lemma 2. That is for every k function v stationary policy. Okay, so I am not proving this for t pi. The procedure is same, and I think you all are intelligent enough to do this on your own. So stationary policy pi and scalar art we have. Okay, so I did some. I was writing art reward function as mu. Somewhere here I have changed. So mu. I think rest are fine. And this scalar is R. Uh, or maybe take it as something else, beta. Uh, then we have TK V plus beta E. So E is basically function from state space to R such that E of S equals to 1 for all S. That means it's a constant function with value 1. This is equals to TK V S plus 1 beta. Sorry, right? Plus gamma raised to k times beta for all S in S. And similarly, t k pi v plus beta E S, that is equals to t a pi v S plus gamma raised to k times beta for all S. So I think this can also be proven by induction. First step is trivial. Base case is basically, it says t raised to 0 Vs equals to s to 0 plus gamma raised to 0 beta. So this means V plus beta so this is V plus Vs plus beta equals to Vs plus beta. That is trivial, right? Then assume induction hypothesis. then T of A B plus delta D. X. This we have to prove that this is equals to okay. We know what we have to prove. Let's not write that. So this is by induction hypothesis, we can write that this is equals to V of sorry T TKV is we can write this here. TKV plus beta raised to sorry, gamma raised to beta. Gamma gamma raised to K beta E of S. This is by induction hypothesis. And this we can write equals to max over actions mu S comma n plus summation over probabilities of P S A summation over S prime times these things. TK V S prime plus okay, I'm missing gamma here plus gamma raised to K times beta. If you simplify this, you can see that this is max. Okay, I'm not doing writing all this. This will take some unnecessary time. You can do this calculation. Pk plus 1 V base plus gamma raised to k plus 1 beta. So this gamma and will be multiplied with this k and it will be k plus 1. Well, so this completes the induction step and we have proved our result. What you wanted to prove. Okay, so we want to show that this algorithm converges, right? So let's jump into that particular proof and where it converges. That's the question, and we'll see about that. Convergence of value detection. For any bounded function. V that maps states to some real number. The optimal value function satisfies. So V has nothing to do with optimal value function, right? V is just any function. Satisfies V star is equals to limit k tends to infinity t is to k v s. So this says something very strong. Says that you take any function, you apply this operator, which I'm calling Bellman operator. You apply this operator again and again on that function, and you will end up in the optimal value function. If the limiting function, limiting iterate will be optimal value function. That's something very strong. If you recall that in our algorithm, we have initialized V0 as all zero function. So this proposition is saying that that is also not even required. You can start from any function. Maybe the convergence rate will be same, but maybe you'll get for better initial value, you'll convert to true value faster. But anyways, it will converge. So let's do the proof. For every positive integer k, a capital K belongs to Z plus denote all positive integers. Initial state S and policy pi. So here it is not necessary to consider this policy is stationary. Let us consider this is non-stationary. Mu0, mu1, and so on. Let's define this function. No, sorry, we're not defining anything. Say this V pi, we can divide into two parts. V pi s is so what is V pi s? We are taking expectation with respect to policy pi and summing all the rewards equals to 0 to infinity or STAT. Can write STAT or just RT. Okay, so gamma raised to T. Given that S0 is smallest. Okay, so this we can write in terms of limit. Actually, we should write it in terms of limit. Like limit t tends to infinity, and this infinity should be replaced by t. Okay. So this we can write into. I mean, given this constant k, which is a positive integer, we can write this sum in two parts. Limit t tends to infinity, expectation pi, first sum from t equals to 0 to capital K, k minus 1. And in the second term, the rest of the terms, limit t tends to infinity, t pi, k starting from k, t starting from capital K to capital T, gamma raised to T, RST 80 with well, if you see this summation, limit t tends to infinity. Just copy. This summation will always be less than uh, less than gamma raised to t, t running from capital K to infinity, right? So, and this is equals to gamma raised to capital K by 1 minus. Now, again, if you see this term V pi is V pi is this we can write in this format, right? Limit. So you need not to write limit. Okay. Expectation over pi summation t equals to 0 to k minus 1 or STAT plus gamma is multiplied plus gamma times summation t equals to k to infinity r. Okay, I'll erase this, but let me write this first. R STAT given ST equals, sorry, S0 equals to S, right? Now, can we write this second term, erasing this gamma instead of gamma raised to t, can I write gamma raised to k and then, okay, gamma raised to t has to be inside the summation. So last one was a little bit wrong. I mean, it was wrong. Uh, can I write here gamma raised to t minus k? And we'll see this is exactly this. T raised to sorry, t equals to 0 to k minus 1. Gamma raised to t uh, r is t a t plus gamma raised to k times v pi sk. Here sk is a random variable, not uh, not a particular state, and it is inside the expectation. Okay, fine. And this is okay. Now let us write this thing. V pi x 0 we are writing yes. So I'm writing here also G pi is in the left side and in the right side. So why I am writing that we'll understand why. So here it's actually absolute value. So this term, I can take this side as well as that side. And this term is upper bounded by, so V by S K, that is upper bounded by uh, gamma raised to, I mean, absolute value of that, gamma raised to capital K by 1 minus gamma. And can write this. Now, if we take limit, okay, first let us take taking max over pi, what we get? We get, by definition, this maximum over V max by V pi is, by definition, this is V star is, right? So V star is uh, minus gamma raised to K, 1 minus gamma. It's fine. Okay, so here I have so here I have I should have written this. And we know there's gamma raised to V star is K. That is also upper bounded by this exactly same thing. So we can just replace this with 2. Okay. And when we take a maximum over pi, then also it's V star is which is less than V star is plus 2 gamma raised to k 1 minus gamma. Now taking limit k tends to infinity, we have V star is well, sorry, I have messed up with it again. So this is your this gamma raised to k. This is your initial value. Here you should write the initial value. So V0 or just V. So recall that you are starting your uh, value iteration from this V, right? So we are replacing this V. We should not write V start there. We are replacing that with VSK. And if the function V is bounded above, say that is bounded by V is absolute value of that bounded above by N. So instead of this, we can write gamma raised to k plus, sorry, minus will be minus gamma raised to k n. And here it will be plus gamma raised to k times n. Well, now it's fine. So here it will be raised to k minus gamma plus n k 1 minus gamma plus n. And inside it will be tk v is now taking limit k tends to infinity. This side it will be v star s. If k tends to infinity, gamma raised to k will be 0, less than equals to limit k tends to infinity tk v s less than equals to again v star s. So these two are same, right? So this limit k tends to infinity, that is sandwiched between v star s and v star s. So this is exactly equals to v star s then, which is the optimal value. So the convergence to the optimal value is proven. Now, similarly, if you apply this t pi operator on any function, it will give you basically, if you similarly limit a tends to infinity t by a v is that will converts to v by x for all v that are bounded. Right. Bounded. Okay, so that was the thing. Well, next, we'll find a condition when a policy will be optimal. That means some condition we want uh, condition C such that if C, then condition on policy pi such that if C, then pi is optimal, and if pi is optimal, then C. So if we verify that property, that condition of uh, a given policy, if we get that condition, then definitely it will be a optimal policy. And for any optimal policy, that condition will be such. It's a both way condition, and we call such conditions necessary and sufficient conditions. So next proposition is to find such condition. So far we have find that if we iteratively apply this uh, Bellman operator, then we'll end up in the optimal value function. That's cool, but what is the relationship with this operator being the I mean, why it's giving you the optimal policy? That's still not clear. So this proposition will make it clearer. Does it say policy phi is optimal if and only if for every state is PV star equals to P. Actually, for every state, we need not to write if PV star equals to P pi V star. So these are two functions, not a value evaluated at any state. Well, so to prove this, what do we have to prove? Uh, the both way condition, right? So we have to prove that one, if P mu star equals to P pi mu star, then sorry, V star, then pi is optimal. Well, so uh, let this condition is true. Let T V star equals to P pi V star. Then So in last lecture, we have shown that uh, in last tutorial, we have seen that V pi is equals to T pi V pi, right? Or
This true only
sorry,
B pi is optimal, no?
no, V
B
pi is the
pi,
value of policy pi, not optimal.
so, uh, okay. V pi is a policy, not
Yeah.
optical, but
Given the
just a
policy, what is the
fixed point.
value?
It is just a fixed point of T pi
Yes, this
or
you can
fixed point
find
of
in
pi.
last tutorial. Yeah.
Okay.
And also from this convergence, that limit, the last proposition, from last proposition, V star is equals to T V star, right? Because when you are at limiting point, so why is it true? Because limit k tends to infinity, k v equals to v star. Now, if you add one more t on it, so the so if you add one more t on it, it will be again the same, right? Limit k tends to infinity tkv, and that is equals to tv star, and it will be v star, right? So yeah, that's true. And hence v star equals to tv star equals to, by the this assumption, t pi v star, and hence we have this relation v star equals to t pi v star. So well, we have to I think prove some uniqueness, because here the problem is if t pi is now here the question is, what if t pi has multiple fixed point? That I think we have to answer. Okay, so say if I try details, to prove uniqueness, let V uh, V and V prime are fixed points of T pi. Then limit T pi V tends to infinity V pi. That is equals to say V. I'm confusing everyone. Say this is we are starting from V1 and it's going to converging V. And say V prime is another fixed point. So when you're doing this, starting it from V prime, limit k tends to infinity, then C limit k tends to infinity, T k minus 1 pi T V prime. So we have assumed that V prime is also a fixed point. So this is equals to limit k tends to infinity T minus 1 pi T pi. By fixed point assumption, this is equals to V prime. So it's impossible that it will be something else than V prime. It has to be V prime, right? So when uh, I'm saying that it will this limit for any V in last proposition we have seen we have proved that for any V limit k tends to infinity T pi k V that will be equals to V pi. Hence this hence V prime will also be equals to V pi. And if I assume that there exist two fixed points, all the fixed points will by this argument, all these fixed point will equal to this V prime. So there is no other fixed point can exist. Hence, this this implies that V start equals to V pi, and hence pi is optimal. And second is we'll assume that pi is optimal. Then we'll show so that T V star equals to T by V star. If pi is optimal, then pi is optimal, then V star equals to V pi. So T V star equals to T V pi. This is equals to V star. Well, so this if J star, sorry, V star equals to V pi, then it implies also that V pi equals to T V pi, right? And this implies V pi is fixed point of Bellman operator. And by uniqueness of the fixed point of Bellman operator, by uniqueness of fixed point, especially what I'm doing is but we have to prove that T V star equals to T pi V star. So V star equals to V pi W. So this was easiest thing. I was doing all the other things. Okay. So this means V star equals to V pi. V star is fixed point of T. V pi is fixed point of T pi. So V star equals to T V star and V pi equals to T pi V pi. And again, V pi equals to V star. So V pi equals to T pi V star. Since these two are equal, so these all the things are equal. T V star equals to T pi V star. That's it. Sorry, there is lots of confusion. Okay. Now we'll show that how fast this will converge. This iterates. Okay, maybe that is not that important. The convergence rate. Rather, we'll go to show this policy uh, evaluation and policy iteration. Okay, let us stop the discussion of value iteration here. So, what we have shown that this value iteration algorithm will give you optimal value, and okay, the interpretation of this proposition is I have not said anything. Let us discuss that and we finish. So, uh, first thing is limit k tends to infinity. This Bellman operator applied k times on an initial value, initial function that converges to the optimal value. Okay. This star is, and this can be any bounded function. And second, what did we do? It is T V star equals to T pi V star since pi is optimal. If this happens, then pi is optimal. If pi is optimal, then this will happen. Okay, so this T V star is equals to T pi V star is. What does it mean? Let us write it. Max over A R S A gamma times P is A is prime V star is prime. This is the left hand side, and this is equals to R S I S plus gamma summation P is A is prime V star S prime. So this A will be replaced by pi of x. Okay, this is what it means, right? So pi of s is nothing but argmax of this inner thing. Okay, yeah, is it clear? And remember, you are returning exactly this policy. whenever you are saying that two value functions are close or you are not updating the policy, then you are returning this particular policy in value iteration, right? Whichever here saying at every step, whichever action is maximizing your this uh, current reward plus gamma times expected next state value. You are seeing whichever action is maximizing, and at that state, the policy which plays that corresponding action, you are taking all such pairs, state action pairs, and that returning as a policy. And that is what exactly pi is. If that happens, then this proposition shows that that policy will be the optimal policy. And for every optimal policy, that property will be satisfied. Okay, so having discussed all this, let us go to policy iteration. The policy iteration is yet another planning algorithm where yeah, you know all this transition probability and expected reward, and you want to find the optimal policy. So it has two steps which occurs iteratively. You choose a policy, you evaluate the policy. Given you have the transition probability kernels and the reward function, you can always evaluate a policy. By now, you know how to evaluate a policy. There are two ways of evaluating a policy, right? You have learned two ways, right? Can anyone of you please confirm that if you know two ways of evaluating a policy? Yeah, just simple question. Uh, how to evaluate a policy? Can anyone of you please answer?
Keep repeatedly applying it until you reach the fixed point.
Yeah, repeatedly apply. Sorry, can you please say it again?
Keep repeatedly applying the policy until you reach the fixed point.
Yes, yes. So we have shown that t, the operator t, if we apply it on any function v, it will give you the optimal value function. But we have also defined this uh, policy evaluation. So we have proved that limit k tends to infinity, tk v equals to v star. Similarly, if you apply this operator t pi indefinitely on some initial value, uh, then you will converge to v pi. So that is one way. So one is this. And another way is matrix inversion. So V is V pi is equals to R S pi S plus summation T S pi S prime summation over S prime P phi S prime, right? So from this, if we write, say, say S is
Gamma.
one,
I think you
two,
forgot
two.
gamma. Right?
this set. This is your state space. So V pi 1. Yeah, gamma and is told. Thank you. V pi this is equals to R. Let me write this as R pi S. R pi is basically R evaluated as pi S. Okay. Instead of S, I should write 1 in R pi mod S plus gamma P 1 pi 1 1 so on P 1 pi this P mod is pi 1.
In case of deterministic policy, this matrix will be full of ones and zeros only. No?
Sorry, can you please repeat?
So if the policy is deterministic,
Yeah,
then
yes, I am considering deterministic policies. Yeah.
so
Help?
this matrix P pi which you have written
Yes.
will just contain ones and zeros, no?
No. So this is not okay. Yeah, I'm discussing that. Just a second. Give me a second. Okay, so what is this? P is a S prime. That has nothing to do with policy, right? Whether it is, I mean, this is just property of the MDP. P, you give state uh, action and state triplet. I'll give you this probability.
Okay. So policy basically is like you
Yeah,
deterministically choose
policy is basically
a action.
helping you to decide the action. For this
Okay.
deterministic, it's much simpler. It will be like this. For randomized policy, you'll be basically having multiplication of two matrices. One matrix is for MDP, another is for the probabilities of given a state,
Choosing
what is
choosing
the
an action.
probability of taking actions. So
Like like
that will
like
be
like
used.
epsilon greedy could be one policy of choosing an action instead of a greedy action.
No. So here so yeah, epsilon greedy is basically like a randomized policy. I agree, but what I am saying is so epsilon greedy comes in that will be coming in randomized RL algorithm. So now let us not think about that. It's just you have a policy and you have the MDP. So a policy will induce a transition matrix. I mean, when you have a policy fixed, the probability that ST plus 1 will be S prime given S T equals to S, that will also be fixed. Given it is, I mean, whether it is uh, deterministic policy or randomized policy. Okay. Given policy phi, this is fixed. And exactly this thing, these probabilities we are writing here in the matrix.
Okay.
Okay, so then what it means that V pi satisfies a particular equation. And that equation in the if we write in say vector notation, V pi r, this is the vector r pi bar again, so vector matrix P pi and multiplied with P pi bar. So if you solve this, okay, gamma is multiplied here. Sorry, taken it forward. So if we solve this, then V pi is basically I minus gamma P pi inverse R bar pi. So that's how you can compute V pi. Okay. So there are two ways. One is apply the operator T pi again and again, and you converts to V pi. And another is just do this matrix inversion and solve for it. Okay. So that's how we do policy evaluation. So what I was telling, that policy iteration algorithm has two parts. You first begin with a policy pi, say pi 0 for at time 0 or iteration 0. You are beginning with policy pi 0 and you are evaluating the policy. That means you are evaluating. So begin with pi 0, evaluate v pi 0, then this is most important part. Update pi 0 to pi 1. And then again evaluate v pi 1 and so on. So you there are two steps. One is evaluation and updation. I don't know whether updation is proper English word, but hope you understand. So we update the policy,
I think in the
evaluate the
class
policy,
they
and
call it improvement, evaluation and improvement.
yes, I'm coming to that. Yeah. So uh, this update of the policy will make sure that P pi k plus 1 is that will be greater than V pi k is for all s. And that's we want to maximize the values, right? And that's why we call it improvement.
So one question here is in the equation above, you have written V bar pi equal to R bar pi plus gamma times that transition matrix then V. So does that R needs to be subscripted by pi?
Sorry,
Isn't
R,
yeah.
what did you
So
say?
that R, so the R, right, expected reward, right, that is independent of pi, no? That is,
No, no,
or
no.
it
So
is,
when you are fixing the policy, R is say, so I'm considering R is a function of state and action. So say you are deciding at state S1, you will take some action A5. Okay. So this will be always whenever you will encounter state S1, you will always get reward R S1 A5. Right. So pi has a role. Is it clear?
okay, okay. I was just wondering, because here, okay, okay. So because the expected reward, so if there are like, let's say 50 policies,
Just a second. I cannot hear. Maybe I'll get a earphone. Just a second. Okay. Am I audible?
Yeah, yeah.
Oh, yeah. Yeah.
So, what I was thinking was, uh, if if the expected reward is dependent on the policy, then how how, how would you get like the information of that even before in a MDP? So you're evaluating every policy and you're updating the policy. So if that R is dependent on policy, how that information will be available? Shouldn't that be independent of any policy? That R bar?
No, no. R is you have this function R is A. So R is a function from is A to TX. And this you know. Okay. You know the policy, which is for the timing, let us consider stationary deterministic policy phi, which maps from state to action. Now, when you are applying this policy, whenever you are at state S, you will always take action phi is, right?
Right, right.
So this R phi is a function of S. I'm defining a new function, R phi, which maps from state
Okay.
to reals, such that R by
So
S
you're
equals to.
so once you remove that A from so basically you're removing that A from the round brackets and writing it as R pi S.
Yes, yes. Yeah,
Okay. Okay.
that's
Okay. Makes sense.
yeah. So this improvement evaluation step you have understood and so discussed. Uh, the main thing here is the improvement step. Right? How we are updating the policy. We are updating the policy as follows: phi k plus one is R max. Is we are playing some other policy earlier, that is phi k. So if you recall that we have evaluated the policy pi k and then we are doing the improvement step. So when we have evaluated the policy, we have p pi. This is coming from evaluation step. Okay. And you know R, you know P. And all. So what does it mean? That given that from the next step onwards, you will apply policy pi k. What is the best action you can take now? Okay, so this pi k plus 1 is giving you that action. Now, what we are claiming that it will, I mean, the value of the policy, updated policy pi k plus 1 will be greater than value of the previous policy, that is pi. And why is that so? So V pi k plus 1 is that satisfies this equation. This is coming from fixed point of t pi k plus. This equation is from them. And also from improvement step. So R is pi k s plus gamma p is pi k s is prime pi k s prime. And I'm writing this thing pi s pi k plus 1 plus now tell me which one is big. So I have written one thing is first line, one thing in first line, and another thing in second line. Uh, tell me which one is big, which one is larger.
So the second one has to be larger, no, because it's an improvement.
Yes, because that is taken over max. So
Yeah, argument.
this action is corresponding to maximizer. But pi case is not the maximizer. If these two policies, I have to assume that they are different policies. If they are
So,
same,
but
then
at every point, you're saying that we essentially by that equation we get a fixed point
which
of that policy.
which
So in the evaluate step, essentially we are getting a fixed point of that policy, is it?
in evaluation step we are getting fixed point of pi k. So we are at kth step. Fine. We are
Okay, okay.
getting a fixed point of
But
pi
in
k,
the
which is v pi k.
but that is not the case in value iteration. Every point is not a fixed point, right? That is every. But in here,
No, no, no.
necessarily in the evaluation step, every point is a fixed point, and you
Every
improve the policy.
what do you mean by every point is fixed?
I'm sorry, every v of s, the vector v of s which you get, right?
Yes, yes. So yeah, so every step we are doing this evaluation of a policy. In value iteration, we do not evaluate a policy.
But this v pi k of s, it is a fixed point in every iteration when you evaluate for that particular policy.
Yeah, if evaluation of a policy is that is
That
always
itself is, yeah,
uh,
that itself is just a fixed point. Okay, okay, okay,
yes, yes.
okay. Good. But same is so basically we are not evaluating the policy in the value iteration. So that means that there is no fixed point going on at every iteration over there.
Yeah.
We
So
are just calculating the value and
yeah, we are
updating the
update.
policy.
We are applying an operator again and again, and we have shown that
Uh-huh.
that will work.
Makes sense, makes sense. Thank you.
Okay, so as you have said that the second line is the larger one. Well, and by definition, this is V pi Ks, right? That's the definition of V pi Ks, the left hand side. And hence V pi Ks is less than. What is this thing? This is P pi K plus 1 applied on V pi K evaluated at S, right? So if you apply this again and again, so P pi K P pi K plus 1 P pi K S will be P pi K plus 1 square. That means applied twice. So this is coming from the last step. By monotonicity lemma, if you can, in the first you have proven that. Okay. So if we continue doing that, then T pi K plus 1 raised to n. Sorry, and again, we can write for this. This is less than, sorry, greater than V pi K is. And this means if we can apply this indefinitely, V by K is, that will be less than limit K tends to infinity. Sorry, I should not write K. N tends to infinity. T raised to n by K plus 1 V by K is. So this is the policy evaluation operator. Policy eval operator for pi K plus 1. And this is this V pi K is this you can think as initial value, right? And we have seen that if we apply this policy evaluation operator on any bounded function, that will converge to the value of the policy V pi K plus 1. Yes. So we have proven that the value of policy pi K is less than value of policy pi K plus 1. Right? And when we stop this algorithm, so
When the policy does not change.
exactly. And if the policy doesn't change, you can see that this satisfies the Bellman equation. So uh, in that case, it will be, say pi k and pi 1 are the same, then it will be V pi k plus 1 is equals to max over k to a is a plus p prime V pi k plus 1. So this is basically T pi k plus 1, or sorry, T V phi k plus 1 equals to p phi k plus 1 plus 1 is well, that's it. So today we do not have time to code this, but I'll update the IPyNB file that is already uploaded there with the code of policy evaluation or policy evaluation separately, and I'll write two different function. So policy evaluation you can use for other purposes as well. Anyway, uh, and I mean the entire code of policy iteration will be uploaded in the page. Anyone has any question?
I have a question in the assignment. If you can help me out with this. Just one question.
Yeah, sure.
Question number 6. It is actually from so what we have that we didn't cover today, but it is covered in the video. It is about
Okay.
a generalized policy iteration.
Okay.
Question number 6.
Let's just see. Are you still seeing my screen in right?
Yeah, I can see your screen.
Want to unshare it?
I can't see in that. I can't see the assignment part.
Yeah, okay.
Now it disappeared.
Yeah. So it's week 5 assignment, right?
Yeah. Week 5 assignment. Question number 6. It's about generalized policy iteration. So what I understood from the videos about the generalized policy iteration was you could select a random subset of states in both evaluation and improvement. Can you take a look at
Select
the question?
correct state. Yes. API lets policy evaluation and policy improvement interact with each other in a details processes. Okay, I have not seen that lecture video. Which lecture video is it?
Uh, I think
Policy
you.
iteration. That
Yeah.
particular.
It is the second half of the policy iteration. I think it's a small video only, and in the later half he talks about uh, what do you say, the generalized policy iteration. Fundamentally, he mentions that we can have a subset of states evaluated and the subset of states improved, and you can keep going. You don't need to do
Okay.
all states in either of the two steps. And actually, he even mentions that they can be independent. So it may not be very useful to improve upon states which have not been evaluated, but fundamentally they can be independent. You can choose; they can be randomized. The ones which you
Mhm.
use for uh, so uh,
These
so
are
in
sort
the
of
given
like whichever state you visit, you update only that something like.
typically you do that, but he said, well, there is no necessity, well, there is nothing which
Oh,
stops you from,
mhm.
doing the other states as well.
As long
But
as you do update it infinitely often. Okay, so
uh,
that.
so so basically in that he doesn't talk about convergence very well, right? I didn't find good information about the convergence, but in these questions, there are questions on convergence actually.
Okay.
So I guess GPI lets policy evaluation, and you don't have to answer the question, but I'm just saying, according to me, GPI lets policy evaluation and improvement interact with each other regardless of the details of the two processes. I am assuming that's the basic idea of generalized policy iteration, fundamentally speaking. So I'm assuming that statement is true. Before
Oh,
convergence, the policy evaluation step will usually cause the policy to no longer be greedy. So I really didn't understand matlab, uh,
before
that part.
convergence, the police.
First of all, I'm not even sure whether he mentioned that this GPI converges always.
State
So like,
allocations only for second step, I do not really understand. Second option, no longer being greedy. Okay, it's probably saying that you can take any action. Probably.
you can have some kind of an like epsilon policy where you can choose some action with probability. But fundamental thing is he never mentioned anything about the, well, I guess I didn't figure out the convergence of criteria for the generalized policy iteration. Do these policies converge? Like so value iteration and policy iteration generally you mentioned like we did now, they converge, right? That's what, when the functions are bounded, they converge. So I didn't really like hear much about convergence in the lecture of these GPIs, and the three options
So
are about
what
their convergence only. So it is become
what I think this is covered from Sutton and Barton. Uh, Probably you can get the answer there. I'll also search. Uh, if you do not get anything, you can put a mail to
okay,
me.
okay, okay, okay.
Probably it will be there in Sutton and Barton. Searching now.
Okay.
Yes, so read this 104, page number 104. Maybe it will be clear that there are discussion. 2 pages of
Page
there.
number 104. Okay, okay, I'll do that. Thank you.
Okay.
Page
Okay, so
number
we are
one.
104. The version I
Okay.
have.
Yeah,
Yes,
yeah,
sir.
yeah. The
Just control.
there are two pages on the generalized policy iteration. Okay, I'll do that.
Okay.
Thank you.
Okay, so we are stopping recording, and next day we'll discuss Monte Carlo TD learning.
Okay, thank you.
Right.